Okay, so this is a sort of outline of the sort of things I'm going to be talking about today. So mostly I'm going to be talking really about observational things today, and I'll be talking about the models and the theory behind the models in the next lectures. But there's been quite a lot of advances in observational work in planetary dynamo theory. So I'll be talking about dynamos in other planets as well as the dynamo below our feet, although of course the Earth's dynamo is the one we know much more about. So these are basically the things that I hope to get through today, and they really are what you might call prerequisites before you actually get on to interpreting the kinds of models, the kind of dynamo simulation models that we've actually been doing, the theoretical side of it. For a very long time, the theory of dynamos has really been quite advanced and pushing forward, while the observational side has rather tended to lag behind. But in recent years that's been overcome to some extent with the new planetary missions that have been going, which have given us considerably more information about the kinds of planetary dynamos that there actually are out there. In Sweden I remember a little cartoon that Raymond Hyde used to draw. It was a picture of a Viking ship, and on one side of the Viking ship there were huge beefy Vikings with big arms and huge oars, and on their backs it said theory, and on the other side of the ship there were some puny little people who could scarcely lift their oars, and on the back it said observation on their back. The chap at the back of the boat was scratching his head and saying, for some reason this boat is always going round in circles. I don't think why. And that's quite a wise comment, because without the observational input it's very easy to lose track and get onto the wrong kind of theories that are not really quite relevant. So I will be talking about the observations, and also some of the fairly elementary theory which goes behind actually interpreting those observations. So those are the things that I'm hoping to cover. Okay, so here's some pictures of what we've got. Okay, so planets are by and large divided into three classes. They've got terrestrial planets, giant planets, the gas giants, Jupiter and Saturn in our own solar system, and the ice giants, Neptune and Uranus, which have rather different internal compositions, and we'll come to those later. But let's start with the terrestrial planets, because they mostly have rock mantles, like the yellow region there and the Earth there, and many of them have got metallic cores. This little picture here indicates the brown region, which is the fluid outer core, and then there's the solid inner core there, which is the solid iron part of the core of the Earth. And it's of course in this brown region here, this fluid outer core, where we believe that the dynamo is actually operating. That's where the magnetic field is generated. From the Galileo mission, the gravity field of Ganymede was accurately measured, and they deduced a model for the interior structure of Ganymede there, which has also got a core there, an iron core, which is, since Ganymede seems to support a dynamo, is actually a fluid. Now it may slightly surprise you that I'm including Ganymede as a planet, but from the point of view of dynamo theory and indeed the physics of planets, whether it happens to go around the Sun or whether it happens to go around Jupiter is fairly irrelevant. What really counts is the internal structure, and these giant satellites of Jupiter are as large as some of the planets going on the Sun, nearly the same size as Mercury. So Ganymede is believed to have a dynamo, and the Earth seems to have a dynamo, and these generate magnetic fields are generated in those cores. Now let's have a look at the gas giants. Let's have a look at the internal structure of the giant planets, because where it's fairly clear where the dynamo action is inside the Earth, it's certainly inside the fluid outer core. It couldn't possibly be anywhere else, basically. The situation is not quite so clear in Jupiter and Saturn, and its gas giant Uranus is one of the two ice giants, the other one being Neptune. So the gas giants, Jupiter and Saturn, are mostly hydrogen and helium. Possibly they've got small cores, rock and ice core, down at the bottom. That's actually very hard to prove that is the case. Those cores are mainly there because otherwise people can't work out how the planets could ever have formed. But you can't actually see them directly from the gravity field because they're so small compared to this huge hydrogen-helium envelope. Now, these are big planets, so the pressure increases very sharply as you go down into the interior. And with Jupiter, you get a transition region here where you go from molecular hydrogen and helium down to the state which is called metallic hydrogen and helium. And this is essentially a quantum mechanical effect. The pressure is so large here that the atoms are so boxed in close together that they become ionized. Under those circumstances, because of the Fermi exclusion principle, the electrons can't coexist in the same space with the atoms, and so they are separated out, so the electrons are detached, so the material is becoming ionized down here, and those free electrons then give you a source of electrical conductivity. So that although hydrogen and helium are things you wouldn't normally expect to be electrically conducting, nevertheless they are under those conditions. It is possible to reproduce those conditions very briefly in shock experiments. So there are physics high-pressure shock experiments in which the material, hydrogen and helium, is compressed to a very high value for a very short time. But these high-pressure physicists are clever guys, and they manage to measure the electrical conductivity of that state, even though it actually exists for only a tiny fraction of a second. So we do have some information about what the electrical conductivity of this state is. Basically, if you look in Jupiter, then the interior there, where I'm pointing now, the electrical conductivity is not that different from the Earth's metallic iron core, actually. So it's a sort of a similar value, but as you go further out, of course, the pressure declines. And because the pressure declines, then the ionization declines. So you go from a fairly high electrical conductivity down there to essentially zero electrical conductivity at the surface. So there's a sort of transition region around here where you're going from the metallic to the molecular state, at which the electrical conductivity will start to fall fairly dramatically. But it's not, that's drawn there as a sharp line, but it's not really a sharp line. The conductivity is a continuous function, so it gradually drops off from highly conductors in here down to non-conductors up there. So Saturn is basically the same story for its internal structure, but it's smaller, and therefore you have to go deeper before the pressure gets to a level at which the ionization occurs. So that the top half of Saturn is going to be electrically non-conducting and therefore essentially dead from a dynamo point of view, and the dynamo has got to be located somewhere down here. So these planets have strong magnetic fields, so it's also consistent with the fact that they've got electrical conductivities there. These ice giants create more of a problem. The source of the electrical conductivity is believed to be this ionic ocean. It's sort of called an ionic ocean. I'm not sure that's a very good word for it. It's certainly nothing like a fluid ocean. Temperatures are very high. But it is believed that the conductivity here is due to the same kind of effects that occur in seawater, i.e. the passage of free ions. And so this is where the dynamo is believed to be, down here in these ice giant planets. Although it turns out that ionic conductivity is never quite as good as either metallic hydrogen or liquid iron, so the electrical conductivity of these planets is considerably reduced from those there, which means, of course, that the diffusivity eta, which was being talked about in the previous two talks, is at least 100 times bigger in Uranus and Neptune than it is in Jupiter and Saturn. And that has some influence on the magnetic Reynolds number, as we'll see. Okay, so everybody here, is it? So I don't need a microphone? Or?
Ah, that's a good question.
I just wondered, are we all?
God.
I think everyone you can hear actually. That's what it is.
But in the back, it's better, slightly better as a microphone, right?
Oh, okay, that's
Somehow, I didn't even know where I put it. Probably didn't even turn it off.
So let's see. If you put this into a pocket. Okay, oh yes. Makes it even more difficult to go to sleep. Right, okay, fine. So that's got the basic idea of where the dynamos actually are in these regions, and the two ice giants, Uranus and Neptune, actually have magnetic fields, although it must have been admitted that that was quite a surprise because nobody really thought that the ionic conductivity would be large enough to support a dynamo until the Voyager mission went there and actually discovered it did have quite a strong magnetic field. So now let's get back to the Earth and let's have a look at the Earth's magnetic field. So the Earth's sort of fairly typical terrestrial planet, and it's got a mainly dipolar field. Now this picture here is the radial component of the magnetic field, that's BR. But it's not BR as we'd measure it on the surface of the Earth. This picture is a reconstruction of what's measured on the surface of the Earth extrapolated down to the core mantle boundary. So instead of actually this picture being BR actually where we are, this is BR reconstructed at the core mantle boundary. This is a picture due to Andy Jackson. So what do we see in this picture? Well, this is its year 2000. The units, well, these geophysicists nearly always use Teslas and SI units. Since I've sort of been brought up in the astrophysical community and sort of moved into geophysics and back, I'm in a sort of fairly schizophrenic state about this, but I can tell you that 8 Gauss is 8 times 10 to the minus 4 Tesla, and that's the typical field strength at the Earth's magnetic field. So this with 0.8 on this scale here, so you can see from the picture there, we're talking about that kind of field strength extrapolated down to this core mantle boundary, which is of course more than 10 times bigger than it is actually on the surface of the Earth. Now if you look at this picture, what do we see? Well, first of all we see that it is basically dipolar, even though we've extrapolated it down to the core mantle boundary. This up here is basically blue, and this down here is basically orangey red or brown. But we see that it's nothing like a perfect dipole. There are a considerable number of reverse flux patches, and I'll talk a bit more about those reverse flux patches. This one in here and that one in there are particularly interesting. Those ones just below Africa are actually moving westward at the moment, and they're also intensifying at the moment, which means that the overall dipole moment of the Earth is actually dropping somewhat because of these reverse flux patches actually going on. I'll tell you a bit more about that later on. These patches also have a tendency to move westward. In fact, this sort of wave-like pattern here has some kind of a tendency to move westward. The field, however, over the Pacific is much more static and doesn't appear to move much at the moment anyway. Now, within this picture here, you can also see two sort of massive dark blue flux patches up here. That's one over Canada and one over Siberia. And these are the most intense part of the magnetic field. And they also seem to be fairly stable. They don't seem to move very much. Whether they're really long-lasting is somewhat controversial. Some people believe that these things have a lifetime of millions of years and that you can see them back in ancient rock records. Other people are a bit sceptical about that, but it's certainly a possibility that these flux patches here could be really quite long-lived. And there are sort of corresponding things down in the southern hemisphere as well. So we can see it's a sort of basically dipolar picture, but there's lots of sort of fluctuations, lots of noise actually in the magnetic field picture. And I'll probably come back to that picture and talk a bit more about it later on as we come back, because it's a sort of fairly key picture. Okay, now we're sort of moving outwards a bit in the solar system here. Mercury has a magnetic field that was measured quite a long time ago when the first probe went in 1976. There's actually a messenger probe which is right there right now, and it's sort of remeasuring the magnetic field of Mercury. And interestingly, the 76 observations seem to be fairly good. This is saying that the basic dipolar structure of the planet has been sort of confirmed by the first pass by. But it's going to get a lot closer to Mercury, and in fact it will get into orbit round Mercury, so that in a year or so we should know quite a bit more about the nature of Mercury's magnetic field. At the end I'll talk a bit about possible theories for Mercury's field. The most striking feature of it, I think, is this really very low value here, 1.4 times 10 to the minus 7, about 100 times, or more than 100 times weaker than the Earth. And that is in some ways a bit of a surprise. You might think, well, it only rotates 57 days, one period, rather than 1 day period. But we'll see later on that that's actually not really right, that in fact all planets are rapidly rotating. Even 57 days is rapidly rotating when you look at it in dimensionless terms. So that the idea that you could just explain the weak field of Mercury just on the basis of its slow rotation is almost certainly wrong. There's got to be something else going on there as well. And there are a number of other things, a number of proposals on the table, which could account for why Mercury's field is really rather low. Okay, so now we're moving out. Now Venus is in many ways a twin of the Earth, so one would expect a priori its magnetic properties to be quite similar to those of the Earth, and indeed its core structure is quite similar to the Earth, so it's quite a surprise that it's got zero magnetic field. That's something that clearly needs to be explained. Why is Venus not got a magnetic field when the Earth, whose structure, overall structure, appears to be rather similar, actually does have a fairly strong magnetic field? So that's sort of a mystery, one of the first mysteries that comes up in this game. Ganymede has a sort of fairly Earth-like magnetic field. Its inclination, it's basically a dipolar field. Its inclination is about 10 degrees, same as the Earth's. It's much smaller, the core is much smaller than the Earth's core, but if you actually extrapolate the field down to the core mantle boundary, it's not that different from the Earth's magnetic field, a little weaker. It rotates once every 7 days, so its magnetic Reynolds number is not going to be all that large, as we'll see, but nevertheless it seems to be large enough to have a dynamo. Perhaps the most extraordinary thing about Ganymede is that it's got a liquid core at all, because it's quite a small body, much smaller than the Earth, and one might imagine that it would have cooled off and solidified, but it apparently hasn't. And it apparently must have a liquid core, because it's certainly got its own internal magnetic field. Mars, this is another surprise. It was known for a long time that Mars doesn't really have a magnetic field, but the surprise when the Mars Global Surveyor went round the planet was that there was very strong crustal magnetism, much stronger than anything that occurs on Earth. That certainly suggests that Mars had a dipole field in the past. Crustal fields are always small compared to dynamo-generated fields, so we're in nanotesla land here. So we're an order of magnitude smaller than anything actually on the Earth's magnetic field, but nevertheless, for a remnant field, that's pretty big, and so there are sort of regions there where there's a strong magnetic field, and there's fairly coherent parts of that magnetic field as well, suggesting that probably that is the signature of a planet which once had a magnetic field, but no longer has a magnetic field. So that tells us something else, which is quite interesting, which is that dynamos can certainly die. And if your dynamo dies, it's thoroughly bad news, because of course dynamos, the magnetic field of the Earth protects us from the solar wind to a large extent. So once you lose your protecting magnetic sheath, then you're at the mercy of the direct solar wind, and that can do all sorts of horrible things to the planet underneath. Okay. And now we go out. Okay, so we're continuing our voyage outwards. The giant planets are all rapid rotators, and Jupiter has a strong magnetic field. It's got the strongest magnetic field of all the planets. It's basically quite similar to the Earth's magnetic field, except it's got a more harmonic structure. There are more harmonics in Jupiter's field than there are in the Earth's field. And we'll see that there are obvious reasons why that's sort of to be expected. However, Saturn presents another horrendous problem, because Saturn's magnetic field is almost exactly axis-symmetric. It's about sort of about 2.5 gauss. It's a moderate field at the surface. That means it's got a strong field deep down in the CMB, where it's core mantle boundary, where it's down there, where it's actually generating its dynamo. To see that, I've got a little picture there, which is a sort of little cartoon of the dipolar structure. There's a sort of little bar magnet being inserted there, and nice dipole-like lines of force coming out there. But I think this is a nicer picture. That picture there is a picture of the aurora of Saturn. Saturn's magnetic field traps particles coming in from the Sun, just like the Earth's magnetic field, and well, maybe we'll see an aurora sometime here, but that's what the aurora looks like on Saturn. The most striking thing of that little picture is that it really is extremely circular. And the reason it's extremely circular is because the magnetic field going through it is highly axis-symmetric. This causes a bit of a problem, actually, because you'd like to know what the internal rotation rate of a planet is. And the best way of finding out what the internal rotation rate of a gas giant is to look at its magnetic field. Just looking at the surface doesn't tell you very much, because there are very strong winds on Jupiter, some of them going east, some of them going west. So the rotation rate depends on whereabouts on the surface planet you look at. But if you go deep into the interior of Jupiter, it's all rotating much more like a solid body. As we'll see, the typical velocities inside Jupiter are only a bit bigger than those in the Earth, much, much slower than the winds on the surface, so that the interior rotation rate is very, very constant, and the rate at which the magnetic field goes is really well known to loads and loads of significant figures. And people were hoping from the Cassini mission that they would find the non-axisymmetric components of the field in Saturn, and hence work out what Saturn's real rotation rate actually is. But one of the slight disappointments of the Cassini mission is with the field, the closer you look at it, the more axisymmetric it appears to be, and nobody's yet managed to work out what the internal rotation rate of the planet really is, because it's so axisymmetric. Why is that a problem? Karl-Heinz Regler this morning pointed out Cowling's theorem, which says that an axisymmetric dynamo is impossible, a theorem proved first by Cowling, who was a professor at Leeds, actually, a long time ago. Well, I guess Saturn was put there just to annoy Tom Cowling, because there you have a planet that really has an axisymmetric magnetic field. So there's certainly got to be a theory. We've got to try and understand how that field actually seems to be so axisymmetric. And of course, the theory says that the whole field must have non-axisymmetric components, not necessarily just the bits you see. So the most likely explanation is that it's just the bits we see that are axisymmetric, but deep down in the interior it's probably non-axisymmetric, and there's something going on in the region between the dynamo region and where we see it, which is axisymmetrizing the fields. So it's not an insuperable problem, but it certainly is one that needs some thought. Now, not only was it a surprise when Uranus and Neptune turned out to have magnetic fields, it was even more of a surprise when people started to measure what sort of a magnetic field. All the other magnetic fields in the solar system are basically dipoles aligned roughly with the rotation axis, like the Earth's, about 10 degrees off or so. But Uranus has one which is miles off, so there's the rotation axis, which in itself is skewed to the ecliptic plane. So this is the sun is sort of over here in this picture. So unlike the Earth, which is only 23 degrees inclined, Uranus is nearly 90 degrees inclined, so it has very long winters and very long summers. And its magnetic field axis is skewed again, and it's off-centered as well. So it's not even a centered dipole. So in a sense, it's hardly a dipole at all, if it's not a centered dipole. So it's got a very strange magnetic field. And again, there are various theories which we will discuss, which may account for that. And Neptune, the other ice giant, is in the same situation. That also has a weird magnetic field, which is not really a dipolar field, and it's certainly not aligned with its rotation axis. Okay, so now we'll move a bit on to actually describing how you describe magnetic fields. So outside the core, the field is potential, of course, as was explained, with no currents, because the thing is not, the mantle is essentially the non-conductor of the Earth, and there are non-conducting regions of the planet, so we can represent the field as potential if we're sufficiently far away. And these coefficients GNM and HNM are known as the Gauss coefficients, after the man who first worked all this out a long time ago. He was not only a great mathematician, but a great pioneer of geomagnetism as well. So these are the associated Legendre functions here, which are usually taken as Schmidt normalized. That's something which is sort of important if you're actually doing numerical simulations and so on to get that right. And that's just one of the things that's a sort of subject-specific, and geomagnetists have been using this normalization for time immemorial. R is the surface radius, and in this formula. So you can see from this formula that as you go into the interior, the higher harmonics, because of the n here, become more and more important, so that when you go the other way of thinking about it is if you're a long way away from the planet, all you ever see is the dipole. That's the lowest, the n equals 1 mode. You have to go close to the core mantle boundary for the other harmonics to start registering because of this factor here. It also means, the bad news there, it also means that you're never going to be able to work out what the internal fields are that are due to large n components, because by the time that they get to the surface, they are so contaminated by other things. There's, of course, magnetic fields from the sun mess things up. But the worst offender is actually crustal magnetism, that is to say the rocks in the Earth are permanently magnetized to a small extent, and eventually the remnant crustal magnetism makes it impossible to distinguish what is really down at the bottom compared with what is up at the top. But that only affects the higher degree n, so you can get down to about 13 or 14 before n, about 13 or 14 before you run out, and anything higher than that is hidden from view, unfortunately. Okay, so that just says that, yeah, that's about, okay, so that's there. One of the good things about this, the observations is that geomagnetic phenomena are generally on a fairly slow time scale. Things don't happen down in the core in time scales much less than a year, whereas the things that are coming out from the sun, of course, have a much shorter time scale, though it is possible to sort of separate out, to some extent, the solar signals and the ones that are really due to the interior, really due to the Earth's core. Now let's have a look at the spectrum. This is a picture from a famous paper by Langle and Estes, and it's about the Loews-Mauersberger spectrum, which is the spectrum of the magnetic field inside the Earth. And yeah, so I'll just go to one further. Yeah, that formula sort of helps to explain it a bit. So if you take the different m's here, if you stay with one n, so that's n equals 1, they're all the different m's. And in order to construct Loew's-Mausberger spectrum, you square all the different m's and add them together and take the square root, and that gives you the average. That gives you the square of the whole m, and that's the n equals 1 there. And then if you do that for all the others, you end up with this picture. Now let's explain this picture. This one here, this line here, is what it looks like at the Earth's surface. So you can see it's dominated by the dipole up there, and the power in the higher harmonics goes down, so that's n equals 2, that's the quadrupole there, the octupole, and they go down as you go, as you increase n. And then as you go a bit further, by the time you get to this level here, the crustal magnetism kicks in, and so whereas you expect this line to go further down there, actually what you see is this, and this is the crustal contamination. And at this stage it's obvious that any signal from coming down here is going to be completely lost in the crustal magnetism. So that picture there is the core surface picture. And now you extrapolate back to down to the core mantle boundary using that formula that we had before with the Rs over R to the n plus 1, and you see this picture here, this picture there. So of course this has much more in the higher harmonics because the higher harmonics are amplified by that effect from the n plus 1 R to the n plus 1 formula. So you can see the dipole is still dominant, and that's consistent with those pictures I showed you, which even the CMB has blue at the top and red at the bottom. But now you can see that the rest of it is actually fairly flat, in fact. So there is quite a lot of power in the higher harmonics, and one can imagine that this picture could be extrapolated further if it wasn't for the fact that we couldn't see it because of the crystal magnetism. Yeah, it's perhaps worth pointing out at this point, this thing can't be flat forever because the dissipation goes like j squared, whereas this is actually a plot of b squared, and j squared must be, of course, finite because there can't be an infinite amount of dissipation. If you really had that flat, you'd have a sort of ultraviolet catastrophe, so there must be a point at which dissipation kicks in, and those things will then come down. But exactly where that turn down is unfortunately obscured by the crustal magnetism, so that's not something we're going to be able to learn by direct observation. Now let's go back to this picture here, well, the dipole moment. I think we had that formula somewhere in Karl-Heinz's talk. So that's the dipole moment for the Earth, and it's interesting to plot that as a function of time. And you can see that it's currently going down quite fast. That's what it was in 1850 at about 8.5. It's now down to about 7.7. And it's actually decaying much faster than if you had free decay. That line there is the rate at which you would decay if you just switch the dynamo off altogether. If there's no fluid motion in the core, it would decay in about 15,000 years. Along that line there is actually currently going down much faster than that, so it's actively diminishing faster than that. And if you go back, this goes quite a long way back. If you go back to sort of Roman times, so that will be about naught on that figure. We know roughly what the field was then from looking at the magnetic field in pots which are fired at that time, because those pots pick up the magnetism that was prevalent at that time, and so we know that the field is about twice as strong. The dipole moment is almost exactly twice what it is now. So it's more or less halved since Roman times, yes?
Simple question about pots. I don't know if you know about. Doesn't the later magnetic fields in later periods affect the pots in any way?
Well, no. I mean, no. I think the point is that it's the moment at which the thing is fired. And then cools down, because what happens when you fire it is you destroy all magnetism, because all magnetism is destroyed when you get above the Curie point. And then as it cools down through the Curie point, it picks up that magnetism, and it's that magnetism as it cools through the Curie point that is actually registered. I mean, of course, these things are complicated. And there's a huge literature, of course, as you can imagine, about archaeomagnetism, which is the business of actually sorting out the relationship between what you actually measure when you bring it back to your laboratory and what it was actually like in the field. But I think the basic result that the field is dropped by a factor 2 is almost certainly correct. So it's certainly going down, and if you actually look at the plots, you can reconstruct these plots back a surprisingly long way, because people were making magnetic measurements in ships from mariners going around and measuring the magnetic field. So these things can actually be reconstructed properly back to about 1700. And if you go right back to the picture, we had, just flip back to where we were, to that picture. It appears that the reason why it's going down is the intensification of these reverse flux patches here. This is actually what's causing the problem, if you like. That's actually causing the current decline in the geomagnetic field. The things over underneath Siberia, so we're there. The things underneath Siberia and Canada seem to be fairly stable. They don't seem to be going down much at the moment. But of course, one never knows what's going to happen next. So these are the Gauss coefficients for Jupiter and Saturn. And here you can see the dipole is the dominant one in both of these things here. So this is the thing at the surface of the planet. Well, the surface of the planet is not terribly well defined. Conventionally, it's defined at where the pressure is 1 bar. So that gives you a definite answer. And then you can look at Saturn, of course, and I said that the field is terribly axisymmetric. And you can see that's consistent with these numbers here. All these numbers are tiny. They're very imprecisely known, actually, compared with the axisymmetric component. That's the G10 component. The G10 is the dipole aligned along the axis. G11 is the equatorial dipole, so if the dipole was not aligned with the axis but was through the equator, then G11 would be large. And then you can see these figures here. And these actually are slightly bigger than these don't drop off as fast as the Earth's magnetic field, so that the higher harmonics, as I said before, of Jupiter certainly do seem to be larger than the higher harmonics in the Earth. And this is a picture of the magnetic fields of Uranus. Here is a reconstruction of Uranus up here and Neptune down there. And you can see from these pictures that they're not particularly dipolar. I mean, you might sort of think, well, it's sort of got a bit of a dipole like that inclined, but then there are all sorts of bits that don't really fit, and then you try to make the same kind of thing in Neptune's field, and you're lost, really. It's just a complete mixture of all the various harmonics. It's certainly not just simply dipole dominated. Well, here's something we've already seen, so I'll go through this fairly, but I'll just make a few points. I did mention, actually, that there's no magnetism above the Curie point, so if you heat things up, they stop being permanent magnets, and the Earth's core is something like 4,000 to 5,000 K miles above the Curie point, so it's completely impossible that there could be remnant magnetism inside the Earth's core. So the idea that it's a sort of Gilbert's original idea that there was a sort of bar magnet sitting down inside the Earth, unfortunately won't work because it's just too hot. There's got to be a dynamo there. Thermoelectric effects and also a field induced by the solar wind have been suggested as possible explanations for Mercury's magnetic field, partly due to the fact that it's rather small, and so one sort of naturally thinks, well, maybe something different is happening on Mercury from what's happening on Earth, and that's why these ideas have been suggested. Although I think it's fair to say that the sort of what you might call the majority view, I think, amongst the planetary magnetism folk are probably that Mercury is a dynamo. There are just special circumstances which are making its field lower, and we'll describe those later on. So here we are, fluid motion in the core produces it by dynamo action. This is a theory which goes back to Larmor in 1919. I'm always amazed, actually, that it took people so long to come up with this dynamo theory. I mean, Maxwell's equation has been sitting there for years and years. Extraordinary, really, but there you are. I mean, that's what happened. So, the pre-Maxwell equation here, and Ohm's law and moving velocity have been covered by both previous speakers, leading to, with Faraday's law, leading to the induction equation here. So the idea is that the currents are generated by motion across the magnetic field lines, i.e. that term is the crucial term which is actually creating the magnetic field. What's called the dynamo action. And here again we have something, the magnetic Reynolds number, which has been referred to, so simple scaling of the ratio of this term to that term. You just replace that u by a typical velocity, and the curl by 1 over a typical length scale, then the del squared by 1 over a typical length scale squared, just in a very crude fashion. Then the ratio of these terms turn out to be u star L over eta, and that's the magnetic Reynolds number. And the Earth's core magnetic diffusivity turns out to be about 2 meters squared per second. I should say that none of these numbers are known exactly. I mean, some people will still write down 1 there rather than 2. I mean, within a factor 2, there are possible uncertainties. I'll come back to that later. So none of these numbers are known exactly, but their order of magnitude is certainly known. So then we get this figure for the magnetic Reynolds number, and possibly, let's just have a look. Perhaps the most important distinction between planetary dynamo theory and all the other dynamo theories that you'll be hearing about in this winter dynamo school is that in planets, Rm is not huge. You can show that for any kind of dynamo to work, the magnetic Reynolds number must be greater than a number. There's a fairly simple bound which gives you pi squared, so it's got to be bigger than 10. If you start doing numerical dynamo simulations, you usually discover that you need it a bit bigger than that. Typically sort of around 30, 40, 50 is enough for dynamo action. And if you start looking at what the Earth's core velocity is and the Earth's core size, you end up with an Rm of about 700. You might ask me, how do I know what the Earth's core velocity is? Well, I'll come on to that in the next slide. But that is a sort of typical value for the motion speed inside the Earth's core, and it is really, really slow. 4 times 10 to the minus 4 is slower than your average snail, so that's the speed at which it's actually moving. It really is slow, and that's got to be, you've got to remember that. That has a lot of implications actually for everything that follows. So it's really, really slow. So despite the fact that the Earth's core is big, nevertheless you end up with a value of Rm only about 700. If you have a look at some of the other planets, well, Jupiter is quite a bit bigger actually. Jupiter is sort of getting to be in the large Rm limit because the core size is 10 times bigger and the electrical conductivity is sort of similar to that of the Earth. So, and the velocity also, the velocity is about 10 times bigger and the eta is about the same as well. So there are, for various reasons, the Jupiter's magnetic Reynolds number is quite large. So ohmic decay time is not all that long. It's sort of relatively short, a mere 20,000 years. The Earth's magnetic field has been around for 3.5 billion years. That's the age of the oldest rocks which have still got magnetic fields in them. And since the whole Earth is only about 4.5 billion years, that means that the dynamo seems to have been with us almost from the period of formation. And there's no evidence at all that the dynamo was ever off in the Earth. It appears that it's been working away more or less from its formation period. Okay, so I'll talk a little bit about how we get to this U star. And in order to do this, you have to do the process known as core flow inversion. So in order to do this, I said the magnetic Reynolds number is not that large, but what is actually done in practice is to start off, when you're doing this, to ignore the diffusion term. It's not a terribly good approximation, but that's the first idea, basically. So that then the induction equation just has that form. The curl of u cross b can be written like that, provided the divergence of u is 0 and the divergence of b is 0. And since ur is naught and dur is, dr is naught at the core mantle boundary, because it's a no-slip boundary condition, we get the radial component just gives rise to this equation, partial dB by r by dt is minus u dot grad br. So the idea is that we can observe br, that's the field, that's Sandy Jackson's plot that I've already showed you. You can also have a good crack at dBr by dt, because we can see how the magnetic field moves around. It's known how dBr BR has changed over really quite well over the last 20, 30 years when we've had magnetic satellites up there. So we've got a good idea of that. We've got a reasonable idea of that. So perhaps we can reconstruct U using that equation, basically. So you know that, you might hope to be able to reconstruct that. A little more thought, only a very little more thought, tells you that there's a problem because there are two unknown components of U. We can't have any radial field at the CMB, but of course you can have U theta and U phi. So we've only got one equation, so we can never hope to obviously work out what both U theta and U phi actually are. And a little bit further thought tells you that if there's any velocity on a line on which BR is constant, you're never going to see it, because if you're on a line where BR is, there we are, where BR is constant, then the gradient of BR is going to be 0 in that direction. So the directional derivative along that line will be 0.
So sorry, Chris.
Yeah.
Isn't B theta also an observable? B theta.
B theta? No, it's not a direct observable. No. No, you can't. No, because that's.
So the field of the Earth's surface isn't purely radial, isn't it?
Well, yeah, but you only get one. You've only got what the field of the Earth's surface comes from one variable. It comes from the scalar potential. Yeah. Once that's specified, everything is specified. So the field only contains one scalar piece of information now. So you can't get that directly from
But
that.
still,
that
B phi doesn't extend beyond the liquid core, right?
B phi
B
does not.
theta,
No, that's
yeah,
right. No, that's right. It doesn't extend. You can't have a B phi outside.
Yes,
of
but
yeah,
B theta and BR should be penetrate to the.
Oh, B phi. Yes, but they're not independent. That's the trouble. They're not independent.
Okay.
They're not independent. That's the real point.
Yes.
Yeah, they're not independent. So what do people do? Well, they have to make some extra dynamical assumption. You have to make some assumption about U, and there are various ones that have been tried in the literature. Probably the most successful is the one that's called tangential geostrophy. The idea of tangential geostrophy is to say that near the CMB, perhaps the Lorentz force J cross B isn't very important. The diffusive terms aren't very important. The buoyancy is not going to be very effective right near the core mantle boundary. So let's say that the Coriolis force, or more particularly the component of the Coriolis force, the vertical component of the radial component of the Coriolis force, and this radial balances the pressure in that way there. So that then gives you further information about U. So that's a reasonable assumption from the dynamics near the surface, and that is sufficient to give you that extra condition on U. The divergence of cos theta times U is 0. Now we've got enough information, because now we've got a relationship between UR and U theta, so we can now use that other equation, equation 1, the radial magnetic field equation, to produce a map of U, and that is actually what's done, and that is a particular one, yeah. I think that also comes from Jones1a and Jackson, that particular reconstruction there. That's a picture then of what we think the core flow might be. Now these are all, they've got extra assumptions coming from all this crazy tangential geostrophy assumption. And of course there's all the problem that you can't have all the lower harmonics, higher harmonics aren't there because they have to be filtered out. So these pictures are somewhat speculative, but different authors using different techniques and different assumptions nevertheless usually find the same sort of basic kinds of patterns. So there does seem to be something reasonably coherent about this. But really all that I'm going to use this for is for estimating. All I'm really interested here is in the length of the arrows. And the length of the arrows works out at about 20 kilometres per year, and that works out at about 6 times 10 to the minus 4 metres per second. And as I said, that is slower than a snail. So that gives us some estimate of what U actually is inside the core, and that is the estimate which leads to this RM of about 700. An RM of 700 is sort of manageable within simulation. So in a sense, planetary dynamos are, in some sense, easier than any kind of astrophysical dynamo because we're not in this high RM limit. This very tricky high RM limit, which I'm sure we're going to be discussing an awful lot for the rest of this meeting, and it's still very controversial. In a sense, the planetary dynamos sort of short-circuit that because we have values in the magnetic Reynolds number which we can actually compute. Okay.
But still, 1,000 or so is still...
Well, it is tough. I mean, it's tough. I say it can be computed. You need a big computer. I mean, and most of the calculations don't go much more than about 1,000. So it's tough. I'm not saying for a moment it's easy, but it's sort of in the range where one can imagine, as computers improve, that we should be able to get really quite high resolution pictures of it. Okay, so we haven't really seen the equation of motion much, so there's the equation of motion, the Navier-Stokes equation, that's the Boussinesq form of it, which is used in almost all the planetary dynamo simulations at the moment. So here we've got the inertia, that's the rho du by dt, that's the convective derivative there, there's the Coriolis term, which is very important in rapidly rotating systems. We've got pressure gradients, we've got the Lorentz force term, and we've got the viscosity there, and we've got the buoyancy forces there. So there are a lot of forces flying around in these things, but that's what we've got to handle. And of course, I said it's sort of easy to, well, not easy, but it's possible to get the magnetic Reynolds number right. Unfortunately, the dissipation in these terms here, the real dissipation is much, much lower in the planets than anything in any of our simulations. All our simulations have to take the viscosity way above the real viscosity in the planetary cores. So we can't simulate the things directly. Well, for magnetic field strength, what can we say? Well, the very simplest assumption is just to balance the Coriolis against the Lorentz force. That is to say that the dynamo will grow, the point at which the dynamo stops growing will be when this term starts to interfere with the balance, and we're pretty sure that this is a big term, so perhaps it's a good idea to balance that against that. So it's a very crude argument, and we'll see later on actually that in some sense it is actually there are errors in this argument, and it's more complicated than I'm saying at the moment. But let's make the simplest assumption of balancing Coriolis against Lorentz. Then we can write the current in a very crude way as the magnetic field over a length. So that ends up with B squared being estimated at 2 mu, where that's the permeability free space, that's the density, that's the rotation rate, that's a typical length scale, which we take as the size of the core. And U star is the typical velocity, which is the thing we got from the westward drift. But you can also write this in terms of the magnetic Reynolds number, so that in the unit that turns out is this mu rho omega eta, and that's something which can be measured in Tesla or in Gauss. And if you work that out for the Earth's core, the square root of that, that comes out at about 13 times 10 to the minus 4 Tesla, which is about the sort of values we actually observed at the CMB. If you remember, we had a figure of about 8 times 10 to the minus 4 I wrote down for that. So that it appears that B squared is something like that unit. Now you can already see there's something fishy going on, because I said that this Rm is of the order of several hundred, so y isn't B much bigger, and we'll see that later on that actually y is not bigger. Is that assumption that this is just balancing that is certainly not quite correct. In fact, these two terms here are almost in balance, and J cross B is just slightly upsetting that balance. So that's why the magnetic field strength is actually less than that very crude argument actually gives rise to. Now there are a few other things that are rather different about planetary dynamos and solar and stellar dynamos and galactic dynamos. And let's see, some of them are mentioned here. Well, I've said here this thing called the Alsace number we're going to use quite a lot, so that's going to be that's something which is roughly order 1, because I said that the B that's seen on the Earth is comparable to that unit, so that's another way of writing that, is to say that the Alsace number, capital lambda, is roughly order 1, and that seems to be what actually happens in the Earth. So naive arguments give it to be that, but actual simulations give it to be that, and we'll see later on why that difference arises. The primary balance being geostrophic against Coriolis. Right, okay, now a very common assumption in stellar dynamos and galactic dynamos is that the kinetic energy is roughly in balance with the magnetic energy. Now that comes about if the inertia roughly balances the Lorentz force. So in very crude terms we can write u dot grad u twiddles, which means sort of comparable to, in order of magnitude, J cross B. Which really have vertical bars here, it's the order of magnitude, it's the magnitude of course which you'd expect to be roughly in balance. And since there's a y over length scale in both of those, that turns out to give you roughly u star squared, roughly b squared over mu. So that means that the kinetic energy density and the magnetic energy density are roughly in balance. Now, nothing like that is happening in the Earth's core. In the Earth's core, this term, the inertial acceleration, is really rather small compared to the Coriolis force there. If you estimate the ratio of these two, it's the Rossby number here, because you've got u squared over L there, you've got u omega here, so the ratio is u over L omega. So that's the u over L omega times that. And that is very, very small in the core. You can see that straight off, because this snail speed u that we're getting, the very, very small u, means that it's very, very small compared to L omega. So that means that these terms are not in balance at all. It's this one which is the dominant part of the acceleration. The Coriolis acceleration is much more important than the inertial acceleration, certainly on the large scale. Okay, so because that means that kinetic energy is much, much smaller than magnetic energy in the core. So that that means that there's nearly a factor of 10 to the 3 difference between the kinetic energy density and the magnetic energy density. So there's no simple equipartition of kinetic energy and magnetic energy in the core. The fundamental force balance is different in the planetary dynamos. Yeah, Amber.
Does this mean that magnetic energy scales with overall rotational energy rather than the convective energy?
No, it isn't. No,
the energy source is kinetic energy.
No, it isn't as simple as that. Probably by the last lecture I'm giving, actually, no, about lecture 3, I think, we'll be coming back to this, is exactly what does the magnetic energy scale with. And it turns out that it's pretty well independent of the rotation as well. It depends almost in convective-driven dynamos, it depends almost entirely on the heat flux coming out. So the crucial thing which determines the magnetic field strength is the heat flux coming out through the planet.
So this is the energy reservoir which dynamo taps, right?
Exactly, yes. Okay, so those are some sort of basic facts. Right, okay. So now I'll talk a little bit about energy sources. This is again sort of fairly controversial. There are some people that believe that precession and tidal interactions are driving the geodynamo. That's the energy source. The majority view is certainly that thermal convection and compositional convection are responsible. But of course there may be planets where precession is important and thermal convection is not important. We don't know at this stage. Far more work has been done on convectively driven dynamos, but that's in some sense because it's sort of slightly mathematically easier rather than for any sort of fundamental physical reasons. Although it is true that there are problems with precession as a source of the energy source for the dynamo. If you're going to pursue a precession theory, then you write down the equation of motion like that. So that's the Coriolis term, and since the omega p is very small, because the precession axis of the Earth precesses only around once every 26,000 years, so this is very small compared to that. So the important term is this, and that's the source term, and that's the thing which corresponds to the buoyancy term. So if you actually want to construct a precession-driven dynamo code, what you do is you ask somebody who's already constructed a buoyancy-driven code, and all you do is you take out his buoyancy-driven form and you pop in your precessional, your Poincare force, to drive it. So although the theory is different, the actual mechanics of how you go about it is not all that different. But the problem with this is that typically what happens with these kind of dynamos is that you excite high-frequency inertial waves, which have got frequencies of the order of days. Now, those have somehow got to be converted into slow, large-scale circulations, and it's not entirely clear how that can be done, whether indeed it can be done.
What is the source for omega p cos omega?
Omega p is the precession. It's the precession rate. So that's the 26,000 years. You know, the Earth's rotation axis moves around an axis in the ecliptic planes of the pole star. Won't always be the pole star. You know, it moves around once every 26,000 years, and so that's tipping up the core all the time. So that's basically the core is being tilted, and so that's basically the energy source. So it's not in a state of rigid body rotation. Basically, it's not in a state of rigid body rotation. It's in a state where you're combining the rotation, angular rotation of the diurnal angular rotation with this precessional angular rotation. This is very small, but although it's very small, I mean, the power in the geodynamo is not that large, so you don't need a huge term to actually drive that. As we'll see, when the buoyancy force is that if it's driven by compositional convection, the temperature fluctuations are a tiny fraction of a degree centigrade. Is actually doing all the driving. Because these velocities are very slow, you don't need a huge energy source. So it's hard to rule out precession just by overall energetics. The main problem with it is this conversion of time scales. Compositional convection was introduced by Bedinsky in 1963. He pointed out as the Earth cools down, its inner core is actually growing. The dense iron is freezing at the ICB, that's releasing buoyant material. This process is liberating about half a terawatt, 10 to the 12 watts of gravitational energy. A power station typically produces something like 10 to the 9, so it's not huge compared to sort of ordinary terrestrial numbers. And the latent heat is also released during driving thermal convection as well, by this growth of the inner core. So compositional convection liberating light material, which rises up as the heavy material gets deposited on the core. Of course, it releases light material. That light material floats up, and as floating up, of course, turns over the core and produces velocities. It's possible that the thing could actually work the other way around, and maybe it's actually working the other way around in Saturn. Drops of helium are thought to be possibly condensing in Saturn, or sort of helium rain going through the planet, and that is in a sense like a compositional convection. That rain might be coming down and stirring up that particular planet. So there are various slightly exotic formulae. Yes.
So this produces enough large-scale eddies.
Yeah, that produces enough large-scale eddies to get those kind of velocities that we're talking about.
So the composition, it's homogeneous.
The composition it's being released at the inner core boundary. Yeah, so that of course that means that over time, secularly, it's getting more and more light. Yeah. So the way to think of this is when you've got that situation, the best way to think of it is being in a steady state and to imagine that there's a sort of uniform sink, due to the fact that it's going up. So you have then a situation where it's coming in at the bottom and then sort of being absorbed and mixed throughout. So the source is essentially at the ICB and the sink is distributed. So that's the picture, the way to think of that. Okay, well, so when convection occurs, it is very efficient. That's the same as in astrophysical situations, of course. So the temperature is got to be slightly steeper than adiabatic, so it's super adiabatic, but it's only a tiny amount steeper than adiabatic, and it's tiny fractions of a degree are enough to drive the dynamo. So here's a little bit of thermodynamics, so I'll go through this fairly quickly. That's basically the hydrostatic equation from these thermodynamic definitions of the specific heat and the coefficient of expansion. It's possible to work out what the temperature gradient is using the hydrostatic equation. And then you get to this sort of key equation which tells you what the adiabatic temperature gradient is in terms of things which we know about. At least we've got a reasonably good idea of what these are inside the core. So that we have the picture where we've got an adiabatic temperature gradient, and of course heat flux will be carried by conduction down that adiabatic temperature gradient. So we get what's called the adiabatic heat flux. And that's inexorable in some sense because the core is certainly very close to adiabatically stratified. We know that from seismology. And so we know that that amount of heat has got to be conducted along it. And for convection, what you need is the actual heat flux has got to be more than can be carried down by conduction. So the heat flux production to get convection has got to be greater than that adiabatic flux. So even if no convection occurs, it's still conducting down the adiabatic, so the core is still cooling and the inner core is still growing even if there were no convection at all. Though we think there must be some convection because of the dynamo. So that's a picture of what the temperature structure looks like inside the Earth. Here we've got the mantle, of course, that's where we are, down here, so it's near normal temperatures. Then it rises very, very steeply, then gradually rises, and then at the bottom of the core mantle, near the core mantle boundary, there's a boundary layer which is detected by seismology called the D double prime layer, which is believed to be a thermal boundary layer, over which the temperature changes rather quickly. We've got mantle convection, that's plate tectonics going up all through this mantle. That's the boundary layer down there at the bottom, which is in some sense driving that plate tectonics. Along here we've got the adiabatic stratification. That's the close to adiabatic, and down here we're about 4,000, just under 4,000, and up here we're just over 5,000. So the temperature difference across the core is about 1,000 degrees. Okay, so interestingly, if you look at this picture, this is actually slightly steeper down here than it is up there. That's just the way the core structure works out. And of course the radius down here is much, much less than the radius down there. So that means that far more heat is carried by conduction out here, and much less heat is carried by conduction out down here, close to the ICB. So that means that if the heat is being generated input by latent heat production at the ICB, that means if there's 4 terawatts coming out there, it can't possibly be carried by conduction because you can only carry about 0.3 terawatts down there. So there's got to be convection down there. As you get up here, it becomes less and less clear what's going on because more and more heat can be carried by conduction. So it depends rather critically on what the heat budget for the core is. It's entirely possible that this could be stably stratified, that all the heat could be actually being carried by conduction, but it's almost impossible for that to be happening down there. So there must be convection going on down close to the ICB, but perhaps not there. So that tells you something about the dynamo. The dynamo may well be being driven primarily by what's going on close to the ICB, and not so much by what's happening at the CMB. And there's a lot of work being done on that right now. That's a very hot topic in this subject, looking at dynamos which are stably stratified close to the CMB, which is possible.
So why was it initially so hot in the core?
I mean, in formation, these things are very, I mean, the temperatures produced on formation are very high because of the gravitational collapse of the planet. That means your initial condition is one where everything's starting from pretty hot, yeah, and then it gradually cools down.
But the core didn't cool.
The core is still cooling. Yeah, the core is still cooling. That's the most popular theory, I should say. there are, as we'll see. This is the heat budget picture. This is one that Peter Olsen's produced, and there are all sorts of things going on in here. I'll just tell you a bit about some of them. There's the core heat flux. That's what's coming out into the core mantle boundary. There's gravitational energy. That's the compositional convection, because of course as stuff settles on the inner core, that's releasing gravitational energy, so that's the contributing to the heat budget in the outer core. Over here we've got cooling, the secular cooling, which is essentially like a uniform heat source. Over time, though from the point of view of the equations, it's usually modelled as a uniform heat source. This QR is radioactivity in the core. Radioactivity in the core is extremely controversial. It's the sort of thing people really fight over. The question is, there's certainly radioactive potassium is certainly missing in the Earth. There's no doubt about that. It's missing from the mantle where you can actually measure it. There are two schools of thought. One school of thought is that it went out into outer space, and that's where it ended up. And there's another school of thought which is that it got into the core, and that's where it ended up. And it makes quite a difference, because if it did get mixed up with the core, then there would be sufficient potassium in the core to be producing quite a lot of radioactive heating, which would be a uniform distributed heat source within the core. And the geochemists, by and large, didn't like that. They didn't think that it was possible for potassium to be carried down into the core, because they didn't think it could mix with liquid iron, which it can't. But then the people who want potassium in the core said, but it can get into nickel, and then nickel can get into the core. You can imagine there's a very long, complicated story can develop out of that, and it's still quite controversial. But it's definitely a possibility that there could be core radioactivity, in which case it's an extra heating source over and above this latent heat release and secular cooling. And then that turns into ohmic dissipation, and stuff coming out of the inner core, of course, and there's QL, which is the latent heat release there. So these sources are all somewhat uncertain, to about a factor 2, but these are some values which I've put down, which seem to be reasonable. These are the most commonly quoted values, let's say. So about 4 terawatts of latent heat released. Overall, the cooling rate is about 2 terawatts. Coming through the core mantle boundary somewhere between 6 and 12 terawatts. So these numbers they're useful for models, but they're all somewhat uncertain. Okay, I'll just put this down. This is slightly more sophisticated than anything else I've said. This is about the efficiency of thermal convection. It turns out that gravitational convection, although it only releases about half a terawatt, is actually a more efficient source of dynamo action than just pure heating. The reason for this relates to thermodynamics and thermodynamic heat engines. Carnot, sometime I guess in the 1800s, pointed out that it's not possible to get all the heat energy out of a heat engine. There's an efficiency called the Carnot efficiency factor, which is basically the top temperature you're working at minus the bottom temperature you're working at divided by the top temperature, and that gives you a percentage, and that's the best you can actually do. Now, I've mentioned that the core mantle boundary is about 4,000 and the ICB is about 5,000, so there's a sort of ratio. It's only about 20% difference, temperature difference, so there's sort of going to be something like a 20% Carnot efficiency factor. But the way you actually work this out is you write down the entropy balance equation, which I'm not going to go through now. I might go through it later on. So you're looking at the entropy balance, and you need an entropy balance equation and an energy balance equation. Now the energy balance equation is basically that. That's saying the flux in at this ICB is equal to the flux out plus all the sources. That's the latent heat, that's the secular cooling, that's the gravitation, that's the radioactivity, if any. Okay, so that's the basic energy balance. And over here, at the top, we have the more complicated entropy balance equation. There's another source. Sigma is a source of entropy. That's the source due to thermal conduction. Thermal conduction doesn't affect the energy at all, because it just takes energy from one place to another without changing the volume integral. But of course, thermal conduction leads to entropy production, so that's a positive definite entropy source, and that has to be taken into account. But because we know what the adiabatic gradient is, and we know roughly what the conductivity is, we've got a fairly good idea of what that actually is. You can put the numbers in and work it out. And then these are the sources and fluxes and sources and the approximate temperature over which they occur. So, for example, radioactivity will be sort of over a mean temperature averaged over the course. So the thing is really, of course, a volume integral with the temperature on the bottom, so you have to make an estimate of that. Of the dissipation, the ohmic dissipation and the viscous dissipation, which increase the entropy as well, and so there's the temperature at which that is happening. And then there are these other terms here. And when you put that together with the energy, you end up with this formula here, which is essentially the Carnot formula. So this tells you that the dissipation, which is basically viscous dissipation plus ohmic dissipation, but we think most of the dissipation in the core is probably ohmic dissipation. So that is actually telling you how much, that's really the dynamo. Everything that goes down the dynamo route eventually ends up, all the energy that goes down the magnetic route eventually ends up as ohmic dissipation. So that for a sort of good dynamo, we want that to be as big as possible. That means we're getting loads of magnetic field production if that's big. So we want that number to be big. And then we look at the rest of the terms here and we think, well, what's going to make that big? Well, the dissipation temperature will be something, and then midway in the course it's about 4,500. This is something like 4,000, so that's not a very big factor, it's sort of roughly 1-ish. So that means the gravitational energy can more or less turn directly into ohmic dissipation. You've got this loss because of the inefficiency due to conduction. And now you've got these terms here. Now these terms are bad news really, because TCMB is only about 4,000, it's about 5,000, so that's only about 20%. That's something like 0.2. So you can only get out about 0.2 of what you put in latent heat coming through this ICMB. And this is even worse because this is going to be some kind of an average temperature. So this is 4,000 over about 4,300 or 4,400. So that's not far off 1, so that's really quite a small number there. So that's telling you that radioactivity, you have lots of radioactivity to get yourself a substantial amount of dissipation coming out. And similarly, the same applies for cooling. So that's why it's often said that compositional effect convection is in some sense more efficient, because more or less all the energy released can end up in magnetic field and dissipation, whereas because of these Carnot efficiency factors here, nothing like all the heat can ever turn into useful dynamo work. So all these arguments are all one-dimensional arguments. They're based on the structure. You don't actually have to solve the dynamo equations to get to that at all. So these are all sort of peripheral information which is actually very useful. There's something called the Wiedemann-Franz law, physical law, and it relates thermal conductivity, and it says that thermal conductivity is basically linked to electrical conductivity. In fact, they're basically proportional in the cores of terrestrial planets. It's just a feature of physics, that. And you've got this formula here. It does depend on the temperature. So what this formula tells us is that the smaller eta is, i.e. the better the electrical conductivity, then the larger the thermal conductivity is. And David Stevenson has a very nice paradox, which I quite like, which is he says, normal people would think that high electrical conductivity is always good for dynamos. After all, you want lots of electrically conducting fluid, you say, to get a dynamo. He says, no, that's not the case. If your electrical conductivity is too high, yeah, that makes that big, that will make the thermal conductivity high. And if the thermal conductivity high, all the heat will be carried down by conduction, and there'll be nothing left for convection. So that actually, if you have high electrical conductivity in a core, you'll have high thermal conductivity in a core, you won't get any convection, and you won't get a dynamo. So that's a nice sort of slightly paradoxical way of putting it. And it also does show you that planetary dynamos are quite sensitive beasts. If you push the electrical conductivity up too much, you stop the dynamo because you don't get any convection. If you push it down too much, then of course your magnetic Reynolds number goes subcritical and you won't get any dynamo either. So you've got to be in a fairly narrow band of action of electrical conductivity if you're actually going to get a dynamo in a planetary dynamo. And this is probably why planetary dynamos are so diverse. I mean, you go to Venus, there's nothing there. You go to the Earth, which apparently looks much the same, and there it's bombing away. It's because of this sensitivity, I think, that planetary dynamos are always going to be sort of... it's hard to predict them before you go there, because of these fairly critical dependencies. Yeah, I just thought I would talk a bit about the inner core. This is another very controversial and interesting problem about the inner core. First of all, I mean, people are often surprised about why there's a solid inner core there at all. After all, the hottest part of the Earth's core is the middle, and the hottest bit is where you'd expect everything to melt, isn't it? But the answer to that is no, because high pressure also freezes stuff. And it's the combination of the pressure gradient as well as the temperature gradient which is crucial there. So actually the very high pressure in the middle actually overcomes the fact that the temperature is slightly higher there and solidifies the inner core. But nevertheless, I mean, the simple thing is that, of course, as the core is cooling, then you expect the inner core to grow. And as I said, we know roughly how much heat is flowing down the adiabat, so we know roughly how fast the inner core is growing because of that, because we know how fast it's cooling. And if you do the sum, which of course people have done, you come out to the very surprising result that the inner core has only been in existence for about 1 billion years. So it's actually growing quite quickly now. If you extrapolate back in time, about 1 billion years ago there was nothing there at all. The inner core didn't come into existence more than 1 billion years ago, and the Earth's been around for 4.5 billion years, and as I said earlier, the magnetic field has been around for at least 3.5 billion years, so the magnetic field is a lot older than the inner core, if assuming that our basic ideas of structure are correct. So there's a sort of little problem there, because no inner core means no compositional convection, of course. You've got no light material being released, no latent heat, that 4 terawatts, very useful, coming right at the bottom, stirring up, making sure you're getting convection at the bottom, that's all switched off as well. So there's much less heat production. And most of the estimates suggest that all the core heat production could then be carried by conduction, so there's no dynamo. But that didn't happen. It didn't happen because the magnetic field has been there, and we can see it in it's left its traces in rocks going back as far as you look back. And I think that's the main reason why this idea that radioactive potassium actually got into the core has actually come from, because that is a potential heat source which is there all the time and therefore could keep the Earth convecting, the inner core convecting. That's certainly where, that's why it really got revived. It's basically the inner core problem that is stimulated that.
So the temperature gradient is not enough to drive convection.
No. It's you've got certain amount is being carried out along that temperature gradient. You've got to have more heat coming in from some source than can be carried out by conduction. Yeah. So conduction is the enemy. You've got to have more heat there than can be carried out by conduction. So there's got to be genuine sources there. Now, if you put enough radioactivity in there, of course, then you can always make it such that it's too much to be carried by conduction along that adiabatic gradient, and then there'll be convection.
If there is fields which are kind of suppressing conduction radially, but that's, of course, means there's already some magnetic fields.
Oh, well, no. We're not thinking about magnetic fields here at all. We're thinking about really just the overall thermodynamics. We're thinking about the heat budget here. Yeah. So the only question we're asking is the gradient going to be superadiabatic? And we're assuming that if there is a superadiabatic temperature gradient, there will be convection. And that's reasonable. I mean, whatever magnetic fields are going to do, they're going to alter the form of the convection. They're going to alter the nature of the convection, but they'll never stop it altogether. If the heat budget requires that heat, if that heat is coming in, then there's nothing else.
I'm saying, can magnetic field stop the conduction?
Conduction? Oh, no. No, I don't think so. I think the conduction is essentially inexorable. I think that, I think is I don't think there's anything we can do about that. Right. Right. I'll just say a bit about some other terrestrial planets. Now, I'm just going to revise now from what we've learned about the sort of basic nature of the planets and things that are going on. What does that tell us about what's going on? And there are basically three ideas for Mercury's weak field. One is that there's essentially no dynamo, but there's a solar wind which is coming from the sun, which is essentially amplified by the presence of Mercury. So it's there. The idea is it's sort of the Mercury is acting as an amplifier rather than a dynamo, which may be correct because the fields are very weak. They're not much bigger than the solar field that's coming around them. Those who believe there really is a dynamo, there are two of them, two groups of people there. As Mercury cools, then the inner core grows, and so the liquid outer core becomes progressively higher and higher in purity. So there's only a very thin shell of liquid iron is actually left. So basically the idea is that the solid inner core grows and grows and grows, and so you just get a very thin shell of rather impure stuff which can't actually freeze, and so you've got a thin shell dynamo. And thin shell dynamos generally have a higher harmonic content, and if you've got a higher harmonic content, that's a low dipole content, and as you fly by a long way away, you don't see those high harmonics. So that could explain why you end up with a low dipole field. That's one theory. We'll find out whether that's correct, because when MESSENGER gets close to the planet and measures the harmonic content, we'll see whether it's got a high harmonic content or not. The other theory is that the core is liquid, mostly stably stratified, as heat is mostly carried by conduction, just as I was saying. Then the dynamo is only close to the ICB, so this theory is that basically almost everywhere it's being carried by conduction. The dynamo is only acting very close to the inner core boundary of Mercury. So then there's a huge stably stratified region around it which is electrically conducting, which of course is shielding the dynamo that we actually see. So all we see is what's the dynamo near the ICB being heavily shielded by this massive stably stratified liquid iron. So although the field strength will be quite high, right down at the ICB, by the time we see it, it's got to have filtered right through all that stably stratified conducting material, and so we see a weak field. So that's the other theory. That's the one I would favour at the moment. But that theory, of course, will say that then the higher harmonics will all be filtered out by this solid core, so that if MESSENGER finds a very low harmonic content, this will be favoured. If it finds a very high harmonic content, then that will be favoured. Okay. Venus. Well, why doesn't Venus have a magnetic field? Well, the answer appears to be basically because it's got no plate tectonics. If it's got no plate tectonics, that means that the core mantle boundary heat flux is limited. You can't take out more than considerably less than being carried out by the Earth. So if there's no plate tectonics, that could reduce the flux through the core of Venus, and then everything could be carried by conduction in Venus's core, and therefore it's stably stratified throughout. So there's no convection in Venus's core, so that's why it doesn't have a dynamo. Well, that's possibly true. That, of course, gives you some interesting speculation.